My name is Mika Peggers. I'm the Product Marketing Manager at Rescale, and joining me today is Leonto Port, our VP of Engineering, and Jesus Hernandez, who does Business Development for Wolfram Research, the provider of Mathematica. And today we'll be doing a webinar called Running Mathematica on the Cloud with Rescale. We're about to get started, but first a few housekeeping notes. We are recording and we'll be distributing this webinar later this week. If you have any questions during the webinar, please make sure to type them in the questions section of the GoToWebinar panel, and we'll address them at the end of the webinar during our Q&A. All right, let's get started. So today, I'll start with a quick overview of the Rescale Cloud HPC platform. One second. Okay, sorry about that. So we'll start with a quick overview of the Rescale Cloud HPC platform and the partnership we have with Wolfram Research. I'll then be passing the presentation over to Jesus, who will introduce Wolfram Research and their software Mathematica. He'll also give an overview of parallel computation using Mathematica and walk through some examples. Leonto will then take over and go through a live demonstration showing how to set up, run, monitor, and post-process your Mathematica computations on the Rescale platform. And then we'll end with time for some questions. Okay, so let's start with an overview of Rescale. Rescale provides a comprehensive turnkey platform for running simulations and other high-performance computing workloads on the cloud. There are several key elements to the Rescale platform that we think make computing on the cloud really powerful, easy, and safe. The first that you can see here is the software. We support a wide range of over 180 different software packages that are pre-installed and tested so that our users can have one unified cloud-based platform to execute all of their simulation work. The next key feature of the Rescale platform is our range of hardware. Rescale is a multi-cloud solution, which means that we partner with several infrastructure providers, including AWS, Microsoft Azure, and others, and that gives us and our customers access to over 36 data centers around the world. It also means that our users can leverage a wide range of different hardware types, including InfiniBand and GPUs. Next, we have an intuitive interface that enables engineers and scientists to set up and execute different types of simulations with an easy-to-use workflow, which Leonto will soon demonstrate. Users can monitor their simulations and results in real time and can do pre- and post-processing directly on the platform with our desktop feature. With our enterprise solution, we also have an administration portal, which allows IT and management in larger enterprises to manage and monitor their usage and to set additional budgets, permissions, and controls for users within their company. We can also integrate the platform with existing on-premise hardware so that IT and management can have transparency and control over all of the resources being used at their company. And finally, we take security very seriously at Rescale, so we've built in many security features into the platform, which I'll come back to again in a few slides. Okay, now I'll dive a little bit deeper into our hardware offering. As I said, Rescale is a multi-cloud environment. We partner with public cloud providers, including AWS, Microsoft Azure, IBM Cloud, and others, to give our customers access to 36 data centers around the world, which in turn gives us a wide selection to different hardware configurations to our users. Because we operate on top of the public cloud providers, that means that every time they update their hardware, our customers have immediate access to the newest state-of-the-art hardware as well, including specialty hardware types like low latency InfiniBand and NVIDIA K80 GPUs. We've also partitioned our global network into 5 separate regional platforms that allow our users to keep their data within one geographic region if they need to. We have 2 of these dedicated platforms in the US, one of which is for ITAR-controlled work only, and we also have dedicated platforms in Europe, Japan, and South Korea. As I mentioned, security is really important to us at Rescale. We have many measures in place to ensure that the platform is secure and that our users' information is protected at every step. We voluntarily submit to regular independent security audits to meet both strict security compliance and regulation requirements. We also encrypt all of our data users' data both in transit and at rest, so it's never unencrypted. And when simulations are running, they are run on isolated encrypted clusters. There's a lot more to say on this, so if you'd like more details on how to keep your data safe, please contact me at the end of the webinar and we'll schedule a detailed security review. In addition to our hardware and software selection, we also offer a straightforward workflow to execute simulations. And we also have our desktop feature available for pre and post processing that allows users to open up a remote desktop to visualize their results directly on the platform. We also have customized workflows available, including a DOE framework. And finally, if you should run into any issues while working on the platform, we have a strong support team of cloud and CAE experts who are available to live chat and help with any issues that users may be running into. Okay, now I'll pass the presentation over to Milyanto and, to Jesus, who will discuss how to use Mathematica on Rescale.
All right, thank you. I'll be able to share my screen here in a second. Hello. I hope everybody can see my screen, that I'm sharing the correct one. If so, it should be saying something like running Mathematica on the cloud with Rescale. Excellent. So what I'm going to do real quickly is first give a quick overview of Wolfram Research, just to give a little bit of background, and then dive a little bit into how one would do some parallel computations using Wolfram language inside of Mathematica. So Wolfram Research has been around for over 3 decades now. A lot of people primarily know us from 2 of our products. One is Mathematica, which was our flagship product used for computational tasks, used for research in industry, commercial purposes. It's essentially this general programming platform. And also Wolfram Alpha, which is kind of a natural language interface to a lot of knowledge-based knowledge and information. I'm not going to spend any time on Wolfram Alpha. We're going to spend primarily on Mathematica and Wolfram language, but I thought the background would be helpful. So to kind of kick things off, we'll first start talking about what parallel computation means in Wolfram language. So within the Wolfram language, there's some jargon I'm going to use, in particular talking about kernels and things like subkernels. So what happens is within the Wolfram language, there's this high-level parallel language interface that basically takes this master kernel, or the controlling kernel, and it splits up a computation and sends it out to remote kernels or subkernels. These kernels work on the computation and send the result back to the master kernel. Essentially, there is no communication that occurs between the remote kernels. There's a way to kind of force a syncing between remote kernels at particular instances in time. If you want to do that, of course, you're going to get a bit of a performance hit in doing so. So the most applications that I've seen and the most useful parallel computations that can be done are ones that are, kind of easily parallelized, where there's no cross effects that need to be accounted for. So I'm going to walk through a couple of the functions that you will most likely encounter when doing parallel computations inside of Mathematica and using the Wolfram language. So controlling kernels is actually pretty easy. There is a function called launch kernels, which will explicitly launch all the kernels that have been configured for your system. Right now, as I launch this for you inside of this Mathematica notebook, this is on my laptop, so you're only going to see, for example, when I say launch kernels, it's going to launch 2 kernels, because this happens to have 2 physical cores on it. When you're within the Rescale system, depending on the configuration you've decided to choose, that'll determine the number of kernels that you have. It'll be closely tied to the processor count. And so in this case, I can explicitly say the function here, processor count, will return how many physical processors that the operating system is reporting back. So in this case, it's 2. I can explicitly say I only want to launch 2 with this particular command, where I do launch kernels of this particular processor count. And it's going to go through the process and launch those kernels for me. You can see the list of running kernels via this command called kernels. And this will kind of give you an indication of what we have up above here. And so in this case, because I've done launch kernels again, I have 4 kernels running. And then you can kind of see here that the number of kernels you run is not necessarily tied to the number of physical cores you have, but I would recommend that you do, which is why I recommend doing something like this, where you have launch kernels, $processor count. But of course, when using Rescale, a lot of this kind of complexity will not necessarily have to be used. A lot of it's going to be taken care of automatically by a nice package that's been created. But I want to show you this just so you have, if you need to get into some of the lower level things, you can see it. You can see the number of kernels with this kernel count, and then I can close kernels with this close kernels command. So what that basically does is it goes through and shuts down all those kernels that I just started. I'm going to do a quick overview of some of the common parallel functions. So within the regular Wolfram language, there's a function called do. If you want to do something in parallel and have that computation split and set across to all the various subkernels, you would do parallel do. Similarly, there's table, which has its analog of parallel table, sum with parallel sum, map with parallel map. There's a couple others, but these are the most commonly used ones. There are functions that are a bit more specific, and I might spend a little bit more time talking about these briefly. So for example, there's parallel evaluate. What that basically does is it evaluates expressions across all kernels. So inside here I would put an expression, for example, and it would take that expression and then send it across to all the kernels. So you would end up with a result that's a list that's the answer of that evaluation across all the various kernels. There's parallel try of an expression, and what that tries to do is it'll evaluate this expression across all the kernels and it'll return after the first successful result. That could be useful. That could be useful for instances, let's say, when you have an optimization process and you wanted to try a lot of different methods or a lot of different starting points. You could parallelize across all the various starting points, but you only are really interested in the first one that returns back. So parallel try would be useful for that. The next two are kind of lower level, parallel submit and wait all. What those allow you to do is to kind of queue up things to submit them, and then wait all basically evaluates those. For the most part, in the Rescale system, parallel submit and wait all aren't going to be quite as useful. You'll probably primarily be using things like parallel try, parallel evaluate, and the functions I include up above. One thing I did want to spend a little bit of time on is talking about how do you create something so it's ready to be put into the Rescale system or to be evaluated in general. A lot of times, if you're familiar with Mathematica, you're familiar with this notebook interface, and you most of the time write your code inside of these and you do these shift-enter evaluations to make sure they evaluate. Once we're in the Rescale environment, we're more in kind of a script mode, in which case it's going to be reading not necessarily from notebook, but from a package file or a WL file. And those are kind of evaluated slightly differently. Let me show you what something would look like. So the way you would kind of do this, you'd do File, New, and then you choose Package. What this is going to create, it's going to pop up a little window that looks like this, and let me shrink that in just a little bit so you can kind of see what it looks like. And in here, you're going to put your code. So if I wanted to do something like 2 plus 2, for example, this code will get evaluated, and then if I have something like plot sine of x from 0 to 10, then this will get evaluated, and it runs from top down. Now, the reason I talk about doing it this way is in particular you want to make sure that this cell over here is a code cell. And this is some subtleties that we can answer questions on later on down the line if there are other questions about that. But basically, to make the transition from a notebook to sending it to Rescale really easy is you want to make sure you put it in a .wl file or a package file. And let me get that out of the way and continue on. So let me show you very quickly some example codes that we want to send to Rescale, and then Mulyanto will be able to show you how you're going to go through the process of pushing this through the Rescale system. So let me bring over here an example of a WL file that I've created already, and I'm going to briefly walk through just what each line of code is basically doing. The important thing here isn't to necessarily understand all the code I've written down, but just to kind of get an idea of the workflow that's involved here. There's a little bit of prep up here where I'm talking about I don't want to allow an internet connection. That's just, I generally tend to put that in here. I'm launching kernels. The next part is I'm going to define a function which counts the number of points that are going to be inside a circle of radius 1. So I should back up a little bit and tell you what in the world I'm actually doing with this, is I'm going to do a Monte Carlo simulation to estimate the value of pi. In order to do this, what I'm going to do is I'm going to drop down a whole bunch of random points in between -1 and 1, and I'm going to do pairs of points, and then I'm going to find out how many of those are actually within a radius of 1. And then when I look at the ratios, that'll give me an idea of how to estimate pi. So I can do this serially, in which case what I do is I just literally take, let's say, 1,000,000 points. I'll multiply by the number of kernels I have, so maybe this would be 2,000,000 points. I figure out how many of them are inside, and then divide it by the number of points I had before, and multiply it by 4, and that'll give me an estimate of using pi. And right here with this absolute timing, this is just for later on down the line. I want to see how long did this particular evaluation take. This was using the normal kind of evaluation sequence. And in fact, it's so normal I don't have to use the function evaluate here because it's implicitly doing that. But if I want to do this in parallel, I'm going to use the function parallel evaluate. You'll notice that everything else looks essentially the same, except now I wrapped it with parallel evaluate. I'm going to take the total of it, so I'm going to add all those various pieces up, and then I'm going to divide it again by the number of points it actually had. So this takes the 4 million or however many points I decide to take and split it up across all my subkernels, and then combine the results later on down the line. So I have an S pi, which is a serial estimate of pi, and then a P pi, which is a parallel estimate of pi. What I'm going to now do is take S pi and P pi, put them in a table, and export it to this .dat file. Now, what's nice about the Rescale system is that all the this concept of where files are going to live, where they're going to go, they all live within their job queue, and so I can just simply write it like this, and I'll get this .dat file at the end that'll be along with the rest of the data for the job. Finally, in this, what I want to do is kind of a slightly different computation. I want to see how does this Monte Carlo estimate of pi converge as I increase the number of points. As you can imagine, when I have only 10 points, this is very quick. When I have 1,000 points, it's also fairly quick. But as I get to 1,000,000, 100,000, perhaps even all the way up to 1,000,000,000 number of points, that computation is going to take a long time. Parallel map is very convenient here because what it does is it allows computations that get done quicker. That'll open up another kernel, subkernel, and that kernel will just go ahead and start doing the next computation. So it doesn't wait for all the computations to get done. It's going to go ahead and keep grabbing all the next ones that it can do that's available. And then what I do is just go ahead and make a data file that shows you what that convergence looks like, and I also make a plot that's going to come out of it. So that's what this Monte Carlo estimate of pi does. And I think if there's time, we might also show another example, and I'll just briefly walk through it. That's slightly different. That one here is pretty mathy, and it goes through and it does some interesting math computations, which are useful to do. But I also want to show an example here of doing something with Wolfram language that I think it's very ideally suited for, which is text processing. So what I'm going to do here is I'm going to import in a list of books. And so I have here, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 books out of the Wizard of Oz series. In fact, there were a whole bunch of Wizard of Oz books that were written and published in the early part of the last century. So what I'm going to do is I'm going to import the text of all of those books, and I'm going to start counting the mentions of character names. And I'm going to note it, and I'm going to try to look to see, as I go through the history of these books being published, what does the frequency of the character names look like. So you'll notice, for example, if we look at the results of this, that Dorothy, of course, in the first few books is mentioned all the time. It kind of dips down, and then towards the end of the series, she comes back up again. And you'll also notice there was a book, for example, The Scarecrow of Oz. Not surprisingly, when you look at it, Scarecrow of Oz, the Scarecrow is mentioned more there than he has in some of the other books as well. But this is doing some parallel processing in the fact that I'm not going ahead and serially analyzing the content of all these books. I'm going to go ahead and parallelize across the books and perform computations independent of each other where I go through and do these character counts. And so with that, I imagine there might be questions about some of the functions I did here, and I'll be glad to answer any of those at the end during the question and answer session. But I think now would be a good time to hand it over to Mulyanto so we can talk about how do I take this .wl file and submit it to the Rescale system.
Okay, thank you, Jesus. So I'm just going to real quickly show how you would run the examples that Jesus just showed on the Rescale system. And so right now, what you see on my screen is the login page for Rescale. So if you want to run Mathematica on Rescale, you'd go to rescale.com, sign up for an account, and then you get brought to this page to log in. And I'm going to log in here. For logging in, for security reasons, we support single sign-on as well as multi-factor authentication. These are some great security features that are optional that you can add to your account. Once you're logged in, you're brought to the jobs list page, which shows you a list of all the jobs that you have in your account, whether they're running or not. And you can see here that I've got one job running and some finished jobs as well. But what I first would like to do is show you exactly how to set up a job, and then maybe also talk a little bit about how you would use a package that we created to parallelize over multiple nodes on Rescale. So the first thing I will do is really quickly run through a simple setup of a Mathematica job. And for this example, I will click New Job here at top left, and I will set up the auth example that Jesus just showed us. When I click New Job, I'm being brought to the job setup page. The first thing I want to do is give the job a name. It's called auth. And the next thing I want to do is upload the files. I can either use files that I've already uploaded to Rescale, or I can upload files directly from my computer. I'm going to upload them from my computer. And here I have the files that are required for this example. So I have the Wolfram language file, auth.wl, and I've got the text of all the books. So I will select them all, and I'll select open, and you can see that they're uploading. And while they're uploading, I can continue setting up my job. Okay, now I'll search for my software, Mathematica, and I select the software, and this brings me to the software configuration page. As you can see, we have multiple versions available. I'm going to use the latest version, version 11. And then I have to specify the commands that I want to run. And it's really easy to select the commands. We already provided with a template of the command, and in this case, it's just Wolfram script or os.wl, which is the name of my Wolfram language file. So after I specify the command to run this job, I next need to specify the license options for this job to use. With our arrangement with Wolfram, it's really easy to run a job because they provide licenses on demand, and all you have to do is click the purchase license button here, and you are set to run the software. The next step would be to set up your hardware, and you can move to the hardware page by either selecting the next button here at the bottom or selecting hardware here on the right side. So let's go to the hardware page. And the last thing I need to do is select the hardware that I want to run on. In this case, I run on 4 cores. Or actually, I can run on however many cores I want to run, but let's say 8 cores in this case. And once I selected my hardware here, you can see on the right side kind of the summary of the hardware that you've chosen. In this case, 8 cores. I got 30 gigabytes memory per server, or on this one server, and also the storage is also displayed here. We of course have many different hardware configurations. In this case, I'll use my general purpose core type Onyx, which is focused on compute. But we also have specialty core types which focus more on either memory or disk space or interconnect, which you can select here from from the core type list. So now I'm ready to submit my job, and I can click on review here. Before I actually submitted my job, let me just really quickly run through what I did to set up the job. I uploaded the input files. Then I went to the software setup, selected Mathematica, selected the version and specified the command that I want to use, and then I selected the hardware that I want to run on. So I'm going to submit this job, and this will bring us to the status page for the job. First thing we do is we validate your job to make sure that your licenses are available, that you have enough budget to run your job. So we have tools to set budgets to make sure that you don't go over a certain spending limit that may be set by your company administrator. And once that's validated, we're going to start the cluster, which takes between 1 and 10 minutes as provisioning your hardware. And at that point, we will execute your job. So while we're waiting for this, let me go ahead and set up a new job and talk a little bit more in depth on how you would parallelize over more than one node. In this case, I'm going to run the Monte Carlo simulation for estimating pi that Jesus showed before. And I will upload this Monte Carlo simulation here. And if we look into the file, what we did with the script, with the Wolfram language script, is we kept the original script. The only thing we added is this needs rescale. Of course, what we actually don't need is this launch kernels here, so I'm going to delete that. So instead of running launch kernels, we run needs rescale, and this will automatically launch kernels for you and make sure that any commands that are run subsequently, such as parallel evaluate down here, will run over those kernels. So I'm going to save the updates I made to the script, and then I'm going to set up the job in the same way I set up the other job. And I have to select the file name here. And paste that in here. Then I have to provide my license. And then here on the hardware setup page, what I will do actually is I will select our smallest node, and I will actually select 2 nodes to run on. And you can see here in the top right, on the right side, that I'm I've got 2 servers, so we'll actually be running this job over multiple nodes. And then I'm going to give this job a name. And then I'm ready to submit my job. And once again, you get brought to the setup page here. In this case, I am actually going to go to a job that has already finished, or that has finished running, but I kept the cluster alive, so you can see what it looks like when your job is running. So here we have the exact same job that I just set up, and it's run over 2 nodes. And what you see here is an extra window of what we call live scaling, and it'll allow you to look at any file that's currently on the cluster. And so one of them is your log, and you can see here that we launched the kernels, and then we ran the job, or ran the script, and the script actually generated these files, including this image file, for example, that I think it shows you the speed it took to run the job. Actually, no, this actually shows you how accurate the estimation of phi is. But anyway, what this allows you to do is look at all the files that are currently on the cluster, and it also allows you to download these files to your local hard drive. So, for example, here I can download this to my hard drive here. And so that's what it looks like on Rescale, how it looks like while you're running a job. And then lastly, what I want to show is what it looks like when your job is finished. Let's go to a finished job here. This is Oz job that is finished. And if you click on a finished job, you get brought to the output file list, and it gives you just a list of files, output files. In this case, what we've generated is a PDF of the occurrences of the characters in each book. You can download it, and you get this plot that is being generated. And this is what Jesus talked about before. You can see the occurrences of each character in each book. But just like this plot, you can download any other file that has been generated by this job. So that's how you run Rescale and Batch. What we also support is, this is how you run Mathematica on Rescale and Batch. What we also support is running Mathematica on a virtual desktop. I think we have enough time for that. I can show you real quickly how we can do that as well. We have got this feature called desktops. And in this case, I've launched 2 desktops here. So I have this one desktop here that I've launched. And when you click on it, you can configure it. I've added Mathematica to this desktop. And what I can do now is connect to it. I'm actually already connected to this desktop, but let me actually go out of this to show you exactly how to connect to it. I will generate a password, and I will download a remote desktop file. So I'll go open that remote desktop file, and then I will have to enter in my password for the desktop. that I have. So I use the password that I've just generated, and that will bring me into this desktop. And as you can see, Mathematica is loaded onto the desktop, and when I click on it, it opens Mathematica. However, let's see, what I also want to show you quickly is how you can actually use a notebook, for example, that you've created. So what I have done is I've created a job that has this game of life notebook that I found online. And so what I will do is go back to my the Rescale interface for this desktop and select Add Jobs here. And I will add this Game of Life job, and then I will apply the changes. And then if you go to the desktop, you can see now that this Game of Life directory was magically created on desktop. And it has this input file, and it has this notebook right here. And when I click on this, it will load the notebook. And then I can just submit this. So this is how you would use Mathematica on Rescale's virtual desktops virtual desktops feature. You can also, of course, run the same scripts, Wolfram language scripts on the desktop as well. If you do not need, say 16 or 32 kernels, you can just use virtual desktops. We provide virtual desktops with 4 or 8 cores, and you can also request desktops with even 16 cores as well. So that's how you run Mathematica on our desktops. So to recap, you can both run Mathematica in batch and on desktops. In batch, we recommend using batch mode if you have scripts that require a lot of parallelization and a lot of compute power. If not, you could also use our desktops offering to run Mathematica as well. And so that concludes my demo.
Okay, so I'm going to take back the presentation because I have one more slide to show. This is just our follow-up slide. I just wanted to point out that today we are offering all attendees a $20 Rescale hardware credit with the promo code Mathematica-Web, and you can use this. If you've already have an account, you can apply it, or you can sign up at www.rescale.com/signup. But we have one more question. The question is, could you talk about using the recently announced NVIDIA DGX1 and Mathematica?
Yeah, so I can add that we do have on our compute clusters. If you run in batch mode, we do have some hardware available that has CUDA installed, as well as the latest K80 GPUs and some other older GPUs as well.
Okay, we've got a few more questions that came in. Okay, one is, how many simultaneous users can you support?
So on Rescale, well, we have a concept of a company account, and so for any given company, you can have as many users as you want. Users are linked to an company email address, so you cannot have multiple accounts over a single email address, but for a single company account, you can have as many users as you like.
Okay, now how do you support ITAR compliance for running applications on Rescale?
So we do have an ITAR-specific platform, and this is available at itar.rescale.com. The hardware on this platform is run on an isolated data center, which is ITAR compliant itself. So in that regard, the hardware is ITAR compliant. On top of that, the data management, the way we handle the files is also ITAR compliant. So the files stay within an ITAR compliant file storage on Rescale.
Okay, well, I think that wraps everything up. I think we had a chance to answer all the questions, but if you'd like to further discuss anything, please don't hesitate to reach out to us. And thank you for joining us today.